Um, Hello. First of all, I want to thank the Clark School of Engineering for inviting me here today. In particular, I would like to thank the Dean of Engineering, Dr. Samuel Graham, also the Chair of the Department of Mechanical Engineering, Dr. Balachandran, and the Chair of the Department of Aerospace Engineering, Dr. Alison Flateau. And of course, thanks very much for the introduction by Dr. Professor Ashwani Gupta here. Thank you. Go to the next slide here. Okay, so this talk is about thorium, actually. But, the word thorium comes from the Norse god Thor, and also Germanic literature, folklore god, which is the god of thunder and lightning and some other good things also of family life, about fertility, etc. So that god, now the Thor that is named after that god as a lifesaver now for our planet. That's kind of the idea here. And that idea is the thorium molten salt reactors. The thorium molten salt reactors that we should really look into for terrestrial use, and also, of course, as I mentioned here, in space and off-planet use also. It is amazing. It can solve several of our problems, like energy deficit, like CO2 production, no CO2 production, pollution, which is the foremost in my mind, actually, and of course the climate issue. So all of those can be addressed with this thorium molten salt reactor, which is what I want to talk about today to you all. So in terms of terrestrial use, as we discussed, I will talk about that for majority of the talk. But for some of the talk, I will also talk about the use of T-MSR, or thorium molten salt reactor, for cislunar space, for moon, for Mars, for propulsion to different destinations within solar systems also. So this is a gift that can solve many problems. I don't like to say kill many birds with one stone, but it's an analogy. Okay, so let's move on to the second slide. What does thorium look like? So this is what it will look like. It's as it comes out of the monazite mine here. This is what it would look like. And the pellets made of thorium look like this, But most important here is that the amount of thorium that we have available in this world in various different countries, the United States being about almost 600,000 ton of thorium. So total is about 6.33 trillion ton of thorium, and 1 ton, of course, is 1,000 kilograms. So that's almost 6 billion kilograms of thorium is what's available on this earth. And that might actually be a low-balled number. It might actually be higher than that. So how much is 1 ton of thorium worth in terms of energy? 1 ton of thorium can produce the same amount of energy as 5 million barrels of oil. 5 million barrels of oil. And you multiply that 5 million by the 6 million that we talked about here, that's almost 30 million barrels. That's 30 trillion barrels of oil. So we have only 1.8 trillion barrels of oil as reserve. This is, as you can see, so much more available here than even those oil. We don't need oil. We don't need coal. We don't need any of those things. And we can have our future with enough energy, or future with no CO2, or future with no pollution, just by using this idea. We need to do this. So what does the thorium power plant look like? It looks similar to other power plants. As you can see here, we have the reactor, but in this reactor, this is the molten salt that we have here in these yellow tubes. And that molten salt is the one that's circulating, continuously circulating. And it contains thorium and then uranium-233 mixed with the molten salt, which can be different types to be decided. That, when it heats up due to fission, it will then go to another heat exchanger where there is another molten salt or any other liquid metal or molten salt, but without radioactive element, without thorium, without uranium. And then that goes to a turbine and heats the water or some other closed loop, and produces electricity. And that's how electricity is produced. So that's how it works. Two things I want you to notice and realize, remember, are this chemical processing plant, which is in between here in the loop, and the freeze plug that is there at the bottom. The freeze plug is very useful also. All right, let's go to the next one. Now, recently, meaning just a month ago, actually, July 18th, so July 18th, Monday, this particular article appeared in Wall Street Journal about is the global nuclear power coming back. So countries are realizing that they can't meet their climate, energy, and national security goals with only the renewable and fossil fuels. So what they are realizing is, since the countries cannot meet these goals with all these things, they cannot meet that without nuclear energy also. So they are now, many countries are now realizing this and going back to nuclear energy as a major solution to their, and rightly so, that we should be doing that. Another article that appeared a couple of months ago in Seattle Journal of Technology, Environment, and Innovation Law is about a couple of very interesting things. The title of the article is Uranium-233, which is bred from thorium, which I will talk about later. The nuclear super fuel that no one is using. Nuclear super fuel that no one is using. Amazing. So why is this super fuel? This nuclear power offers more energy. Nuclear power in general, of course, offers more energy in less physical space, and this is even smaller than the other PWRs. Then the solar and wind and yield more energy per pound than fossil fuel, as I mentioned before. However, different nuclear fuels yield different waste profiles, as we know. This also resists use in nuclear weapons, so it's dilutes the proliferation concerns which exist even today, with 44 different countries having about 440 nuclear power plants in this world already. This results reactions from thorium, which is plentiful, which we discussed, we saw. Additionally, this is a liquid fuel reactor, resulting in safer and more efficient reactor plant than current solid plutonium reactors. And I'll talk about that a little later. All right, let's talk about the possible advantages for this molten salt reactor in general. thorium is abundant, and it is 3 to 4 times more abundant than mined uranium. Mined uranium now consists of 99.3% uranium-238 and 0.7% uranium-235. Uranium-235 is the only one that is fissionable. 238 is not. And so if you just multiply and divide those numbers, you realize that the thorium, which is all of it, is fertile, and so all of it becomes fissionable as U-233. That makes it almost 400 to 500 times more abundant than uranium. That's great. It's fertile, but not fissionable. Fertile meaning you can make that into something which is fissionable. And so it's not radioactive to touch. It goes without saying that there is no CO2 emission here, as we know. And as Andrew McAfee and MIT Sloan School wrote, we are not using our best weapons to fight global warming. This is our best weapon. But unlike CO2 threat, there is one thing which is even worse, and there is the pollution. If you have ever been to New Delhi in India or something, you will realize how bad that pollution is and can be in many places in India, China, etc. This is a real solution where we are not producing, at least factories are not producing, plants are not producing coal plants, no coal plants, none of those are there, would be there. And that amount of pollution that is created with that will be reduced considerably. Maybe not the cars, but then when we have vehicles which are also electric, run on electricity, the electricity created from this would run those vehicles. So this is the answer for all of those questions and things. Next, we have this one. This is a major plus here. Today's power pressurized water reactors, PWRs, whether they are light water or heavy water, they require very high pressure because they don't want water to boil and create steam at very, those temperatures that they'll have to have, 250, etc., that are created centigrade. Because of that, they have the propensity or tendency or possibility of blowing up, and so then we have to have lots of safeguards because of that. Here, we don't need high pressure. The pressure is sea level pressure or 1 or 2 atmosphere at the most. So there's no chance for it to blow up. It's amazing. Then we have this fluid that works. The molten salt is at about 600 to 700 to 800 degrees centigrade. It's this molten salt becomes liquid at about 450 degrees centigrade. Below that is solid. So in that temperature range, about 700 degrees centigrade, because the temperature is higher than the PWRs, the efficiency of conversion to steam, water conversion to steam, etc., for running a turbine is also higher. It's about 45% as opposed to about 30-35% for the other case. So that's also a plus. Then I talked to you about that freeze valve. I showed you that freeze valve. That freeze valve is situated in such a way that if something goes wrong and the nuclear reactor overheats, then this freeze valve will melt, and all of that molten salt, along with the thorium or uranium in it, will drain down into the drain tanks, which are underground, just below. And then once it goes, it'll lose its electricity, heat, and then it'll freeze when it goes below 450. And going below 450 is no big deal. At our 450 centigrade is no big deal. All right, then because of the fact that we don't need very high pressure, etc., these are much smaller plants also, much smaller mass also, and so their application to space also has a huge possibility. The 1% which is produced as a actinide in this case are also usable for medical procedures like technetium, etc., which are produced here, which can be used for diagnostics, medical diagnostics. So it's just like win-win situation here, even more than that. And the last thing is that it doesn't even need to be shut down, and you can read this later on, but it doesn't even need to be shut down because it's continuously flowing. Unlike the pressurized water reactor, we need to be shut down to introduce new rods when the rods run out of the uranium there. So this is it's continuous. It doesn't even have to be shut down. It's just homogenized liquid. All right. Now, there are some possible disadvantages also, which I want to talk about. The material buckling is one of them. The half-life of protactinium, which is 27 days, is also a bit of a problem because that protactinium is now in the same vessel as the uranium-233, which has been produced by protactinium beta decaying. And so then what happens is that any additional neutrons can be absorbed by not just thorium and uranium-233 to fission, but also can be absorbed by protactinium. So the protactinium, amount of protactinium, also increases, and the amount of uranium-233 also increases, and then it kind of reaches a steady state, which is not a good steady state to reach. But, however, the possibility of, so they need to be chemically separated, but the possibility of chemical separation exists. It's an easy solution, actually, because the protactinium, when combined with fluoride, makes it protactinium Pa tetrafluoride, which is liquid, whereas uranium hexafluoride is gaseous. So they can be separated in that chemical processing plant that I showed earlier. So that is a possible problem. There is a radiation protection needed for the gamma rays, which is also a possible disadvantage, and delayed neutrons. But lastly, the problem really is that it's not getting funded. The Department of Energy and this administration needs to take notice of this. I hope so. I really hope so. This needs to be funded. That has been the problem. Other countries are doing it. India is doing it. China is doing it. Netherlands is doing it. Norway is doing it. And I think that South Korea is also starting to do that. So all of these starting to happen. We need to move big way and quickly on this. That is happening. All right. So now let's go to why not the present type of nuclear reactors that we have, which is the PWR, which is LWR, which is light water reactor, or heavy water reactor, HWR. Both of them are pressurized. So they both operate at extreme pressure. They operate at comparatively low temperature, about 350 C compared to this one. They utilize solid fuel technologies and other things. So these are just excuse me. These are just terrible disadvantages. We started working with these LWRs and PWRs because we wanted plutonium at in the 70s and 60s, and for bombs, which was correct thing to decision to do at that time. But now our priorities are different. Our priorities are now energy deficiency, climate change, climate issues, and CO2 production, etc. This is the way to solve those problems now. So, okay, let's go to the next slide. Now, I wanted to also do some calculations, actual calculations here as to what kind of, how much the thorium would be required to run a reasonable sized nuclear plant or any size nuclear plant. 1 ton of thorium, which is 1,000 kilogram of thorium, is 1,000 divided by 0.232, which is the atomic weight of that, equal to this many gram moles now, because it's 0.232 instead of 232. So it's 4,300 or so gram moles. Multiply that by Avogadro's number, gives you the total atoms. Multiply that by per atom release, which is 200 MeV. Multiply that by the conversion factor, joules to MeV, and you get 6.3 10 to the 16 joules per ton. So 1 gigawatt year is approximately this number 8.16 10 to the 16 joules. So as you can see, with this 1 ton, we can produce 2.6 gigawatt per year, or we can have, if you use 1 ton of thorium per year, we'll be able to run a 2.6 gigawatt plant continuously. So it is just quite seriously useful. The world's total electrical need is 55 times 10 to the 9 gigajoules per year. This means that 667 ton of thorium can fulfill this need per year. Considering efficiency of energy conversion, it may be 2 to 3 times more than that. But still, you look at the number of 6.3 million ton that we have, and we are talking about 5,000 to 6,000 years worth of energy. By that time, I'm sure within 100 years, 200 years, or 50 years, we'll have licked the fusion problem, and we will not need. This is a good filler, the best filler, and maybe it can be used also for off-planet use, where we cannot use the fusion for a long while still, or some other places like, where that cannot be possible. So this technology, because of all of those things, just very badly needs to be developed, and the government needs to take real strong action to do that. Let's go to the next slide. Again, this is not really necessary for me to show that too much, but basically this energy, where does this energy come from? Well, it comes from strong nuclear force. The strong nuclear force is what holds the protons together in a nucleus, because you know that the protons repel each other because they are all positively charged. And so this mysterious force called strong nuclear force is the glue that comes from the neutrons, which holds all of these nucleus, the entire nucleus together, and makes it non-radioactive for most part. When it goes off balance, that's when it becomes radioactive. All right, so now this is the force, and then we already talked about what that force is. It creates 200 MeV of energy per atom. This is 1,000,000 times greater per unit mass than chemical, like oil, or approximately oil and hydrogen, etc., RP, JP, methane, etc., and of course 3 million times more in terms of mass, in terms of per unit mass, than coal. So this is a sort of a no-brainer in terms of using it. Again, this I went through already, but I'll just go through this again a little bit. How does it happen? Well, actually, I have not gone through this. Thorium atom, when a neutron is absorbed by the thorium atom, obviously thorium atom is 90 atomic number and 232 atomic weight. When its neutron is absorbed, it becomes thorium-233 immediately. That thorium-233 is unstable, so that will beta decay into protactinium-233, so it loses an electron. It increases the atomic number because of that to 91. Protactinium-233, then atomic mass remains the same. That further beta decays over a longer period of 27 days into uranium-233, in the same manner, losing an electron. And then that one, uranium-233, is unstable, and that fissions. When it fissions, it fissions into xenon and strontium. So xenon and strontium then are created as daughter products, and the energy is released per atom of 200.1 MeV. That's how it happens. While it is doing that, it also releases more neutrons, 2 or 3 neutrons, and that way the chain reaction continues. And that's how the reactor will continue to create energy. This is more or less the same slide and the same things I already talked about. How does it work? All right, now the xenon is, of course, a colorless, odorless noble gas found in Earth's atmosphere, and strontium is something that we take normally every day. However, these are both have radioactivity, and they need to be they have a certain half-life because it's the atomic number is the same, but weight is different. And so, but their half-lives are much, much shorter than the uranium products. It's in thousands of years as opposed to hundreds of thousands of years for the uranium-235 product. Also, I talked about the technetium. Technetium is, of course, here, which is produced here, which is used, as you can see in this green area, that it is produced, it is used considerably in worldwide pharmaceutical use, radiopharmaceutical use. Technetium is used 80% of the time. And here, what it is used for is, various different diagnostics that are done with this. So this byproduct or waste product also is used or useful for other medical uses. All right, so now this particular Thorium-MSR advantage is this. Now, this is an actual thorium molten salt reactor or uranium molten salt reactor at that time that was created by Dr. Weinberg at ORNL, Oak Ridge National Research Lab, and that ran for 5 years and produced approximately 2 megawatt of power at that time, and with spikes of larger than that. This, as you can see, is about a meter in, let's say, meter in each direction, and 2 megawatt. If I want to build a 1 gigawatt reactor, which will be 500 times bigger than this, then we have a cube root of 500, which is about 8. So 8 meter by 8 meter by 8 meter would be the dimension of a 1 gigawatt plant, which is smaller than the PWRs of today. So it's quite amazing. It's just win, 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 win. Okay, now China is already doing this. They've realized this, and they are also doing it, and they have actually built a molten salt reactor in their Wubi province, Thorium Molten Salt Reactor in Wubi province. They have not announced the results of that. They started working on that as of last September, October. They have not announced the results of that, so we don't know. We don't know that. And this is what is being done in Norway. some more development there. And of course, the other countries, like I mentioned, China, India, Netherlands, South Korea, Indonesia, they are all looking at this. All right. So finally, we have for Earth, we have Thorium Molten Salt Reactor would do for humanity of Earth. The solution is available today, with enough supply of thorium to last thousands of years, and with zero CO2 emission. What more do we want? We do not need to build tens of thousands of 1 gigawatt SSP, SBSP, or SSP plants in geostationary orbit, as some have proposed, which is, to me, just no comparison between these two possibilities. This solution then, in that way, has to be developed here, right here in America, in the United States. The time is now for us and for the rest of the pollution-ridden countries to avail of this technological marvel. It's killing millions of people. The pollution is killing millions of people, or they are shortening their lifespan by decades. It's awful. It needs to be paid attention to. One hopes this administration will pay attention to it, serious attention to it, and find a reasonable path for us, and soon. By soon, I mean within next few months, 6 months, year. Then the same tech that we develop here can be applied for cislunar space, for Moon, Mars, any other planets or something that we want to visit, and for energy on those planets in cislunar space, but also for nuclear propulsion. So again, let me get into that now, the space part of it now. The thorium has been detected on Moon by Chang'e 2 also. 1 kilogram of thorium taken from Earth, remember we talked about 1 ton, which is 1,000 kilogram, which created a 2.6 gigawatt thermal plant. This 1,000 of that 1 kilogram would create 2.6 megawatt plant for a year. 1 kilogram expense per year, hardly anything. Imagine 10 such plants in 10 different locations with 10 kilograms of thorium taken from Earth and associated salt, which will eventually become self-sustaining because of this lunar thorium that exists on different places. And I'm talking about sometime in future, not soon, but maybe 20 years from now, or 30 years from now, we can have a self-sustaining energy production with this. And before that, before we go and start finding and bringing it from other places, we can just bring that much thorium from Earth, small amount. Only the first such plant will require neutron-producing radioactive material to commence the chain reaction. After that, the uranium-233 thus produced will provide any further neutrons for additional reactors. It can be done. So for power on the Moon, or maybe Mars, or cislunar space, Geo, MEO, LEO, traveling within that and all that, this is a really interesting possibility of energy production also. All right, so now let's look at the space propulsion part. The space propulsion part here is, I'm comparing it to NERVA here. This is the what is being done, which was being done for NERVA, for example. And this is the chemical propulsion. Chemical propulsion right now, the best ISP, effective specific impulse that we can get is 453 from SSME, and a little bit higher, 461, 462, if you increase the nozzle expansion ratio to very high, 200 or 150, instead of the 75 or 77. that we have for SSME. So in that case, that's the limit that we have, 462 approximate limit. For NERVA, when you are heating hydrogen gas, liquid and then gas, in the nuclear reactor, pebble bed, rods, pebble bed, whatever, nuclear reactors, we can heat it to high enough temperature that it will produce higher than the chemical combustion temperatures. And it's only hydrogen now, that it will produce ISP of the order of 880, 870, 860, something of that order. Now, in this case, for molten salt reactor, we have a limitation of, at least for now, we have a limitation for material, for pipes that this will flow through. And that limitation is 1200 degrees centigrade at this point in time, maybe 1300 or 1400 centigrade at the most, with seasick material. And if we can make it with that, then with even 1200, we can get 665 seconds. Now, that obviously is less than NERVA, but NERVA has a lot of heavy equipment and parts that would be required that this one would not. And so with the considerable reduction in size and weight compared to NERVA type solution, the MSR may be more attractive at system level. This is something that we need to do an analysis on. I don't know the answer to that for sure, but this is just a feeling that I'm expressing based on previous experience. All right, so how is this done? Here in this rocket is the upper stage of New Glenn. So New Glenn's upper stage uses, of course, you know, that B4 engines, which is the hydrogen-powered engines, hydrogen-powered engine, anyway, 3 or 4. Hydrogen-powered engine, which is hydrolox powered engine. So this is the hydrogen tank here on the top, which is the red one, and the green one is the LOX tank. Instead of the LOX tank now, supposing we get rid of the LOX tank, we move the hydrogen tank farther front and put the MSR, the Thorium Molten Salt Reactor, here. Then we have a nozzle here through which the hydrogen would the hydrogen will be heated first through this particular heat exchanger, which is not radioactive. Hydrogen is heated to the maximum temperature that it can, expands in the nozzle, and creates thrust. So these nozzles will, of course, have to be obviously, resized. Not a big deal. So this can be done in this way. And the other major advantage of this is that once you do this, you take, say you have this the rocket. In this rocket, you have the TMSR, Thorium Molten Salt Reactor. You take that to the moon surface, and you have the reactor here. You repurpose the reactor. You take out the reactor and you put that elsewhere, and you can create then electricity with that reactor. You have taken these other parts with you, and you can create electricity with that reactor, the same thing that was there in the rocket itself. Or you can create, instead of creating electricity, you can create the heat. It can heat the lunar regolith or ice, and we can repurpose this. In this case now, the temperature doesn't have to go up to 1200 or 1300 degrees centigrade. 600-700 is fine, which will be, we reduce the exposure and the possibility of corrosion on these pipes. So all in all, it really is quite useful to do. So in summary, I'm going to stop here. So finally, in summary, to summarize all the most exciting points of this lecture for the seminar, the US and the world terrestrially, this thorium offers immense supply of energy that can last several thousand years, with no CO2 emission and no pollution, no pollutants, none, unlike coal or any other. No high pressure explosion possibility, as I showed earlier, none. Twice the efficiency of conversion to electricity, SPWR, twice. Natural and fail-safe freeze valve mechanisms available. Less than 1% radioactive waste products compared to 95% for PWRs of today. No plutonium is produced at all in this reaction mechanism. No plutonium that can be used for nuclear explosives. It does not need to be near a water supply. Today's PWRs are all, if you realize, they are all near some kind of water supply, whether it's a river or lake or ocean. Not needed here. It can be in a desert. Sahara Desert can have this plant. Any other desert in Southwest, anywhere can have that. It can be refueled continuously with chemical processing in the loop without having to shut down the PWRs. So immense supply, no pollutants, no explosion possibility, higher, twice the conversion efficiency to electricity, fail-safe mechanism, less than 1% radioactive, which is amazing. What more do we want? What more do we want? It's an amazing promise, amazing solution. And to not take advantage of this now would be a real shame. So I respectfully urge this administration to take this idea very seriously, and provide funding for it, at least for research and development and engineering to begin with, at least. Let's solve all these problems, and let's solve that with the help of institutions and universities, and provide funding for them to do that, and then we'll go to the next step. Let's start small and go to the next step afterwards. So that's my humble request to the administration. Lastly, since I'm here at University of Maryland giving a talk, I would like to suggest a few things that can be very useful for the university to do, maybe as a contract or a grant or whatever. A computation for ME department, from mechanical engineering department, a computational analysis to assess the heat transfer in heat exchangers. Build a small, 30 centimeter dimension, 30 centimeter by 30 centimeter type, 3D printed simulation, but no reactor for now, to confirm the containment, the pipes and the heat exchangers, that they can work for a long time and they can be sustained and not corroded over many months, maybe a year. Containment pipes can be made using some of the new materials that has been developed by, at least I know, GE CSIC material being suggested for hypersonic flights, etc., for high-speed flights. For the aerospace engineering department, I would obviously suggest many possibilities here for research topics for cislunar and moon Mars travel. They are very promising, which can be analyzed by students through research topic, graduate students through research topics for master's PhD, for their thesis topics. Then topics based on repurposing of nuclear TMSR, which I showed, a rocket for energy on moon and Mars, there's, must be explored and papers published, and this could be very exciting for the new space age that we are going through now for students. Then it's also possible to fly this vehicle on Mars. Mars has atmosphere, or 100th as thick as Earth, but regardless, it has atmosphere, so we can heat that atmosphere and make it go through the nozzle, heat it with this T-MSR, make it go through the nozzle, create thrust, and have a vehicle that can fly. 10 milligram of thorium or uranium-233 would be able to fly this vehicle that we designed one orbit around Mars. 10 milligram. I mean, compare that to the amount of propellant, chemical propellant that we require to do that. It's immense. It would be immense. Here, 10 milligrams would do that. If you take a few kilograms from here, you would be able to, do a lot of things, which can be done for future colonies, Martian colonies, or even before that, for experimentation, for mapping, and then later on for transport. So all in all, just amazing possibilities here for mechanical engineering department, aerospace engineering department, and if we have a nuclear engineering department, which is my last request here to start back, revive the nuclear engineering department here at Maryland University School of Engineering, partly centered on thorium molten salt reactor. That's my humble request, and humble request to university, and humble request to the administration in the previous slide. Finally, I would like to end with this painting that I made of first woman on Mars must go gingerly. As you can see here, she's going so gingerly and just like a river flow here, and so gingerly as to not impact, not affect the topography of Mars or climate of Mars. Let's call it that. Certainly topography or geography of Mars. So with that, I thank you very much for listening. Thank you.